Newton's first law, the law of inertia, applies to rotating objects. Rotating objects tend to keep rotating, while non-rotating objects tend to remain non-rotating. The resistance of an object to changes in its rotational motion is called rotational inertia. It takes a force to change the linear state of motion of an object. In a similar way, a torque is required to change the rotational state of motion of an object. In the absence of a net torque, a rotating object keeps rotating, while a non-rotating object stays non-rotating. Like inertia in the linear sense, rotational inertia depends on mass. But unlike inertia, rotational inertia depends on the distribution of the mass. The greater the distance between an object's mass concentration and the axis of rotation, the greater the rotational inertia. When the mass is close to the axis, it's easy to rotate. When the mass is far from the axis, it's difficult to rotate. By holding a long pole, the tightrope walker increases his rotational inertia. This makes him less likely to rotate and fall. A long baseball bat held near its thinner end has more rotational inertia than a short bat of the same mass. Once moving, it has a greater tendency to keep moving, but it's harder to bring it up to speed. Baseball players sometimes choke up on a bat to reduce its rotational inertia, which makes it easier to bring up to speed. The short pendulum will swing back and forth more frequently than the long pendulum. The long pendulum has more rotational inertia and doesn't swing as easily. For similar mass distributions, short legs have less rotational inertia than long legs. Short legs can move more quickly than long legs. You can change the rotational inertia of your legs. You bend your legs when you run to reduce their rotational inertia. Bent legs are easier to swing back and forth. When all the mass m of an object is concentrated at the same distance r from a rotational axis, then the rotational inertia is I equals mr squared. When the mass is more spread out, the rotational inertia is less and the formula is different. Which will roll down an incline with greater acceleration, a hollow cylinder or a solid cylinder of the same mass and radius? The answer is the solid cylinder with the smaller rotational inertia, because the cylinder with the greater rotational inertia requires more time to get rolling. Inertia of any kind is a measure of laziness. The cylinder with its mass concentrated furthest from the axis of rotation, the hollow cylinder, has a greater rotational inertia. The solid cylinder will roll with greater acceleration. Any solid cylinder will roll down an incline with more acceleration than any hollow cylinder, regardless of mass or radius. The human body can rotate freely about 3 principal axes of motion. Each of these axes is at right angles to the others and passes through the center of gravity. The rotational inertia of the body differs about each axis. Rotational inertia is least about the longitudinal axis, which is the vertical head-to-toe axis, because most of the mass is concentrated along the axis. A rotation of your body about your longitudinal axis is the easiest rotation to perform. Rotational inertia is increased by simply extending a leg or the arm. An ice skater rotates around her longitudinal axis when going into a spin. In A, the skater has the least amount of rotational inertia when her arms are tucked in. In B, the rotational inertia when both arms are extended is about 3 times more than in the tucked position. In C and D, with your legs and arms extended, you can vary your spin rate by as much as 6 times. You rotate about your transverse axis when you perform a somersault or a flip. A. Rotational inertia is least in the tuck position. In picture B, rotational inertia is 1.5 times greater. In picture C, rotational inertia is 3 times greater. Finally, in picture D, rotational inertia is 5 times greater than in the tuck position. Rotational inertia is greater when the axis is through the hands, such as when doing a somersault on the floor or swinging from a horizontal bar with your body fully extended. The rotational inertia of a body is with respect to the rotational axis. A. The gymnast has the greatest rotational inertia when she pivots about the bar. B. The axis of rotation changes from the bar to a line through her center of gravity when she somersaults in the tuck position. The rotational inertia of a gymnast is up to 20 times greater when she's swinging in a fully extended position from a horizontal bar than after dismount when she somersaults in the tuck position. Rotation transfers from one axis to another, from the bar to a line through her center of gravity, and she automatically increases her rate of rotation by up to 20 times. This is how she's able to complete 2 or 3 somersaults before contact with the ground. The third axis of rotation for the human body is the front to back axis, or medial axis. This is a less common axis of rotation and is used in executing a cartwheel.